Okay, good afternoon, good morning, good evening, good, happy, whatever it is, Year 12s. First of all, I want to welcome 12B who are now joining us in our flipped learning adventure. And I also want to introduce you to our new topic, which is mechanics. So we've finished with materials completely and we are moving on to mechanics. And we need to start by talking about vectors and scalars. So in this series of lectures, you're going to be able to state definition of scalars and vectors and list some examples. You need to be able to draw scale diagrams of vectors given their magnitude and direction. And you need to add vectors by using two methods. The first one is scale diagrams, and the second one is resolving them into horizontal and vertical components. As a reminder, for those of you who are new to this process, you should pause this video and take notes whenever appropriate. When the video pauses and asks you questions, you need to answer those questions to the best of your ability. And then in lessons, we will be putting all of this into practice. So the main idea is to make sure you have notes that you can use in lessons. So starting with scalars and vectors and knowing the difference between the two, you've got two lists here. One is made up of scalars and the other one is made up of vectors. And I would like you now just to quickly vote on which one you think is which, please. Hopefully that was just a little bit of recap from GCSE. You did learn the difference between speed and velocity at GCSE if you didn't specifically learn that it was the difference between scalars and vectors. Speed, of course, just has a magnitude and is therefore a scalar, whereas velocity has a magnitude and a direction, and so is a vector. Key difference: scalars only show as size or magnitude. You are now A-level students, you should be using the word magnitude, whereas vectors have magnitude and direction. Just to put this into a little bit of context for you, in Despicable Me, there is a villain called Vector, and he always talks about the fact that he has size and direction. This is the little genius here. So, vectors, size or magnitude and direction. To give you some decent definitions that you can write down, here they are. I'll leave them up there for you. You should write these down, please. Okay, so a nice way to think about the difference between scalars and vectors is to think about displacement and distance. You can see here by road there are many routes you can take from home to school, some shorter and many longer. However, once you arrive at school, your displacement from home will always be exactly the same. So the distance travelled will have varied. You might have walked longer or shorter, but the actual displacement from home will have a size and a direction. I just thought I'd put this on a little map and show you what I mean. So if you live up here on Lime Walk, you could walk to school this way, you might walk to school this way, you might, for some unknown reason, decide to walk to school this way, and you can see that they are all different distances. But actually, if I were to calculate your displacement from home, you would have 0.8 mile displacement in a west-southwest direction. So you've got size and you've got direction there. So we need to be able to do various things. The first one is you need to be able to draw vectors. And the best way to think about this is to think about forces and GCSEs. So all vectors need a magnitude and a direction. You should be familiar from GCSE with these kind of diagrams. I've got forces acting in one direction, and I might have a force acting in the other direction. And the size of the arrow is telling you something about the relative size of the forces. So 50 newtons here, bigger force, so therefore the red arrow is much bigger than the 20 Newton force here. And the direction of the arrow shows you the direction that the force is acting in. Now, at A-level it gets a bit more, not complicated, but a bit more sophisticated. So it's not enough to just have a bigger arrow and a smaller arrow. You need to measure those arrows. They need to be proportional in scale. So for example, if this one was 5 centimetres, how long would this other line here be? Another nice simple question there. Hopefully you got that if that line is 5 centimetres, this line should be 2 centimetres long. So it's not enough to just draw longer arrows. You now need to start using scales accurately. You also need to include arrows, and it's the arrow on the line and also its angle, either from the horizontal or from the vertical, that matters. So the length of the arrow must be proportional to the magnitude, and the arrow, the direction of that arrow, and the angle generally to the horizontal, but you will be told in the information, indicate the direction. This matters because if the arrow was in the opposite direction, the angle to the horizontal would also be different. Notice that this is a much bigger angle. You might be given the angle from the vertical. They would say anti-clockwise or clockwise. You need to take careful attention to the information they give you when you're drawing vectors. Okay, the main thing that you need to be able to do with vectors is you need to be able to add them. And there are three fairly simple ways of doing this. This is all, in fact, all of mechanics is all about just following methods rigorously. So I know some of you like to do things in your head and then just write down the answer, but for mechanics, in order to get marks and in order to get things accurate, you need to be writing it down. The first method of adding vectors is simple scale drawings. This is really very easy. The only way you'll make mistakes is if you're not accurate with your drawings. Second way is using Pythagoras and trigonometry. Now, Pythagoras and trig you have come across at GCSE. This is a fairly easy method as long as you can remember those relationships. So if you can't, now is the time to go away, look them up, write them down, practice using them lots. Practice that GCSE maths. And then finally, resolving vectors. Again, this is actually fairly easy as long as you can remember Pythagoras and trig, but you do need to put some thought into it and you need to follow a particular method in order to make sure you don't mess it up. Okay, so simple scale drawings adding up vectors. I want to take you back to GCSE again and recap resultant forces. So again, you should have seen a diagram like this. I've got 50 newtons acting in one direction, 20 newtons acting in the opposite direction, and you should be able to see that the resultant force is therefore 30 newtons acting in the direction there. Now I could have drawn this slightly differently. I could have the arrow pointing in the other direction, and this time it would be minus 20 newtons, so it's actually acting in the opposite direction to the way the arrow shows me. And again, I would have a resultant force of 30 newtons. I could also, sometimes you have situations where there is actually only one force acting on it, so my resultant force is that one force, 50 newtons. All of this you should remember from GCSE. Now, whilst at GCSE you were taught to look at those pictures, minus the smallest one from the biggest one and work out the resultant force, what you were actually doing was adding vectors using scale diagrams. It's just you were probably doing the scale diagrams in your head. Now, if the arrows are all acting along the same line, so either along the horizontal direction or in the vertical direction, all you're doing is you're taking the first force, you're then adding the second force, adding its tip at the tip of the other arrow. So I've gone 1, 2, and then you're calculating that distance there, which is 50 minus plus 20, which is 30 newtons. If I had two forces acting in the same direction and then one acting in the opposite direction, again I go arrow tip to base, arrow tip to base, arrow tip to base, and then work out that distance, which in this case would be 50 newtons plus 50 newtons minus 20 newtons, which is 80 newtons. And if you're using accurate scale drawings, you don't even have to do this maths in your head. You could just measure this distance and work out therefore what the resultant vector is. It's that simple. That's what you were really doing. So in other words, line the arrows up top to bottom and then measure or calculate the difference from the start to the finish. If they're not all in one line, it is slightly trickier. So in this case, notice they're not actually perpendicular to each other. I've got one acting in the horizontal direction and one acting at an angle. So they're not all in one line and they're also not acting along the same direction. So I need to do something different. What I do is I take this as my first arrow and then I place my second force or second arrow so that I go bottom to top, bottom to top, and then I can draw a third arrow going from the start all the way to the finish. And if I measure the length of this arrow and this angle here, as long as I've done accurate to scale diagrams, I will be able to work out the length of the resultant vector and the angle of the resultant vector. So in other words, draw the arrows from top to bottom, always top to bottom. Notice I haven't got arrowhead to arrowhead when I've drawn the vectors I actually have. Draw the resultant arrow from start to finish, so this time I'm going from the start all the way to the finish, and then measure the length of that resultant using a ruler. You can measure that angle using a protractor. Key point, rulers and protractors are going to be needed for exams. Now, if they're all in one line, not all in one line, but they actually happen to be at right angles to each other, then we can still do a scale diagram, or we could use Pythagoras and some trigonometry. So notice if I rearrange these arrows, they're perpendicular, they're at right angles to each other. When I then draw my resultant vector, what I have is a right angle triangle, so I can use Pythagoras. And whilst I could measure the length and the angle, if I haven't bothered to draw a scale diagram, I can still work it out using Pythagoras and trig. So hopefully you will remember that the length of the hypotenuse squared is equal to the length of the adjacent angle length plus the length, my apologies, I didn't say that very clearly. It's this, L squared equals 50 squared plus 20 squared. So in other words, L itself will be the square root of 50 squared plus 20 squared. Again, this is GCSE. If you can't remember how to do that, you need to go back now and make sure you do. In order to calculate the angle, it is slightly trickier, but again, it's just GCSE maths. I need to use the relationship between sine, cos, tan, and the hypotenuse, the adjacent, which is adjacent to the angle, and the opposite, which is opposite the angle. The rhyme that I have to remember this is silly old hags cackle all hours till old age. So sine theta equals opposite over hypotenuse, cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. Again, you need to know this. If you are not sure what I'm talking about, please go back and look at your GCSE maths. Okay, just quickly putting it into practice. A man walks 95 kilometres east and then 55 kilometres north. By drawing a scale diagram, or by sketching a diagram and using trigonometry / Pythagoras, can you please work out his resultant displacement? Okay, so hopefully you drew a diagram a little bit like this, and using those relationships you were able to work out that the length of L is 110 kilometres. Notice that's to two significant figures because both of these have been given to two significant figures. Finally, resolving vectors. There's one final way that we can do this. So if I have a vector, I know the angle that it is to the horizontal and I know its length, I can resolve that vector into its horizontal and vertical parts. So this would be its horizontal part because I have to go 2 steps over and I need to go 3 steps up in order to get that as a resultant vector. So I can resolve using Pythagoras this vector here into its horizontal and its vertical parts. These are the relationships I need. So in other words, if I want to know the length of the opposite line, it's going to be hypotenuse times sine theta. And if I want to know the length of the adjacent angle, it's going to be the hypotenuse times cos theta. Please, 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 I'm not going to say this again. Go back and look at your GCSE maths if you are not sure what I'm doing here. Okay, so when we can resolve the angle into a horizontal component and a vertical component. And I can then use these components to work out the overall resultant vector of various vectors. So if I've got multiple vectors at different angles, I resolve each vector into its horizontal and vertical part. I add up all the horizontal parts, I add up all the vertical parts, put the horizontal and vertical parts back together, and then use Pythagoras and trig to find the overall resultant vector. That sounds complicated, it's really not, but it is best to draw diagrams when doing this. I suggest pausing here and writing down those steps. Okay, so I just wanted to put that into practice to show you what I mean. Here I've got 3 vectors, A, B and C. And C is neither horizontal nor vertical, it's at an angle to the horizontal. I'll call that angle theta. So in order to add all these vectors together, I need them all to be horizontal and vertical. So I need to resolve C. So now I've replaced C with its vertical part, which is C sine theta, and with its horizontal part, which is C cos theta. I can then add up all the vectors going in the horizontal direction, so that'll be C cos theta minus A, going in the opposite direction, and I can then work out that total and draw that as a line here on a new vector diagram. I can then add up all my components in the vertical direction, which would be C sine theta minus B, and I can draw that as a line. That's my horizontal and my vertical line. And then finally, I can draw a line connecting these from start to finish, and that is my overall resultant vector of these 3 vectors here. Okay, so I just want to finish by asking you to take a look at these 5 vectors and find out how many ways you can come up with to combine them in vector diagrams that will give the same resultant vector. Thank you.